Okay, good morning. Welcome back. Happy Friday, everybody. Today is class number 11. Today is the day that trucks are due. So if you have trucks finished, throw it right in the folder right now for me. And again, I'll take the projects late, but there are penalties associated with it. So throw it in the folder right now. Now is the time when it is on time. Today we are going to cover the second derivative. This is our last day of new material before the test. Monday coming up is our review day for the test. The test is Wednesday of the coming week. Questions on the calendar? Oh. What about the projects? No, the steel drum and pipeline I'm going to assign on Friday. Yeah. Yes, I will hand you 2 brand new projects after the test. Okay, all right. Okay, so let's get started on page 68 of the big packet. I do have a little bit to say about the test today, but we're going to wait for some strugglers to come in this morning. So on page 68, daily summary. In this class, we calculate and interpret second derivatives. Number 1, for y equals x cubed minus x, we're going to find y of 2, y prime of 2, y double prime of 2, and y triple prime of 2. This y of business is really an abuse of the notation, but I'm hoping it's clear that we're thinking f of 2 and over here f prime of 2, okay? And the reason I'm using y is that we're going to be doing some graphing calculator stuff today, and the calculator uses y, it doesn't use f. Okay, so let's give this a shot. Y of 2 is, we'll do it after we do all the derivatives, actually. Okay, so what is y prime in this case? 3x squared minus 1, right? Okay, and now for the first time together, we are going to calculate a second derivative. 3x squared minus 1 is a function in its own right, and we can take the derivative of 3x squared minus 1. What is the derivative of 3x squared minus 1? 6x. And a very natural way to denote the second derivative is to put 2 of those little primes, right? 2 apostrophes up there. And if we can take a derivative twice, then nothing stops us from taking it 3 times. Just take the derivative of the previous answer. What's the derivative of 6x? 6. And then what's the fourth derivative? 0. And then all the derivatives after that, -0. Okay. So the primes become unwieldy after 3. So typically we would do this. If you just put a 4, it looks like a power, but if you put it in parentheses, it's a derivative. Yeah. Okay, so let's start calculating these things evaluated at 2. All right, so first one, this guy here, y of 2, that's going to the original function is 6, right? 8 minus 2. Okay. Y prime of 2 going to the first derivative, right? Plug 2 in there, we get 11. Okay. Y double prime of 2, plugging 2 into the second derivative, is 12. And then y triple prime of 2 is 6. It's 6 no matter what number you plug in for x, okay? All right. So I'm going to do some calculator stuff here. I'm not expecting that you're going to type it in at this moment. I'm just going to do it quick, and I can lend calculators today in class. Yeah, Andra. Great question. What does the second derivative tell us? What does the third derivative tell us? We're going to explore those questions today. Good. Okay, so we're going to find y prime of 2 on the calculator. Again, don't worry about necessarily following along. So on the home screen, here's the notation on the old operating system. It's inside of the math function, and it's way, way down. It's right there, number 8, n deriv. So we hit enter there. We got to type in the function that we wanted the derivative of. That was x cubed minus x. And we put a comma. Then you put this x. That's sort of weird, but we just put it every time. comma, and then what's that 2 represent? Yeah, we're taking the derivative and evaluating it at 2. And we hit enter. What are we expecting was the first derivative at 2? That was y of 2. We're looking for 11 here. Okay, and so we hit enter, and do we get 11? We didn't get 11. The calculator doesn't know calculus. It doesn't know that the derivative of this function is 3x squared minus 1. It's doing secant lines that are really, really close to the tangent line, and it's getting a number really, really close to the right answer of 11. Okay. All right, so there's the first derivative. We can play the same game on GeoGebra. I'm not going to do that just yet. Let's keep playing with the calculator here. To get other derivatives on the calculator, it's actually not terrible. Again, I'm going to do this kind of quick, and you can, scientific calculator, as far as I know, typically doesn't have derivative capabilities. Okay, so I'm going to type in my original function here, and then I'm going to go into y1. Wait a second. I did not follow my directions. So I said to go down to y0 for the original function. It'll just make it cleaner to figure out which derivative is in which line. So y0 is my original function there. Then I'm going way back up, and y1 is going to be my first derivative. So right there with the cursor there, I go math, and then number 8 we already saw was this n deriv. And I want to find the derivative of the thing called y0. I don't want to type the function over and over again. It's not a terrible function here, but it could be pretty big. I think you've seen this before, but you'll find all the y's inside of vars for variables. You scroll to the right to y vars. First option is the one we want, function. And then there's the list. And the one that I want is way down at the bottom. It is y0. So I hit enter, comma, and then here's the funny notation. X is what we always put there. And then like in the last example, we just put a 2 right now. But I want to know the derivative for any x. So I'm going to put an x there as well. So that's the first derivative, and if I want the second derivative, math 8, I'm looking for the derivative of which function? y1. So r's over enter, comma x, comma x. So there's your second derivative. And then one more time, math 8 r's over enter, and nope, that's not right. Let's try that again. R's over enter. So now we want the derivative of y2, comma x, comma x. Okay, so then we've got all our derivatives there, first, second, and third derivative typed out. And we can ask the calculator to find all of these things just on the home page. Again, go into vars to access that list. So y1 of 2, that's supposed to be the first derivative at 2. What's the answer? 11. Okay, good. And now we're going to ask it for y2 of 2. What's the answer to that one? This one was 12. I don't know if you noticed, it was a brief pause while it was doing some calculations there. It was not the same instantaneous thing we're used to seeing. Okay, so it actually hit 12, perfect, that's great. And then finally, what's the answer for the next one? The third derivative is 6. Nope, it's illegal nest. So the calculator has a limitation. It can't go past the second derivative. Just too many nestings. Derivative of was too much for it to handle. Okay. All right. Part E here says yet another method with the graphing calculator out. It says we're going to graph this function. So I'm going to come in here and I'm just going to start over. So we're going to go into y equals, everything's cleared now, and we're going to type in x cubed minus x. That's our original function there. Oops. And I'm going to graph this guy. Yeah, we'll take a look at the graph first. So looking for the derivative at x equals 2, which is this spot right here. What did we say the derivative was? 11, so that's the steepness. Actually, 2 is right here. So the steepness at this point, 11, that seems reasonable to me. It's pretty darn steep there. So here's another option on the calculator. We can go into calc, which is right above trace, second calc. And we can select number 6. And we've seen this Leibniz notation for the derivative, dy dx. And then it's actually not clear that it wants you to tell it an X value, but that's what it's waiting for right now. You can scroll around here, but scrolling around is imprecise, right? I can't just pick an X that I'm interested in. I just get the predetermined ones that the calculator wants. So I can just type in an X right now, even though it doesn't look like it's waiting for me to do that. So the X I'm interested in is 2. And when I hit enter, it's going to say no problem. Do IDX is 11 point lots of zeros at a 1, and it puts the dot right there on the curve. Okay, so this is yet another option to find the derivative. What about do IDX?
The function on the calculator, that will draw up the graph.
I hit graph beforehand. Yeah. Okay. All right. I think that's good. So unfortunately, I did, yeah. What I put in there was on the home screen was this guy up here. Is that what you're asking, or are you asking? Yeah, I just typed it directly in, and then just hit enter there. Oh, that's down here. Yeah, this is what I did on the home screen the second time. It was y1 of 2 and y2 of 2, and that gave me all these derivatives here. It is. It could be anywhere you want. I just wanted to put the first derivative in y1 and the second derivative in y2. So I just wanted to get my original function out of the way. That's all. Okay. All right. So Matt asked this question, which we've answered now. After 3 derivatives, it's kind of awkward to write all the primes. So you can put the 4th derivative up there in parentheses. Also over here on an F instead of on a Y. This part is something that troubles a lot of folks. So you guys, you know the dy dx notation for the first derivative. And so is there anything in here that bothers some of you? What about the 4? It's what? It does, yeah, it could look like x to the 4th power. Yeah, on the top, the 4 is after the d, but on the bottom, it's after the x, which just feels like not fair, right? It's not symmetric. And so the reason that we do that is that we have been talking about how this symbol means the derivative of, and then it's waiting for something. And maybe the something is y, and you just put it up there. But really, by itself, that means the derivative of, right? So if I'm looking for the 4th derivative, then what I really want is the derivative of, so that's 2 derivatives, and then 3 derivatives, and then 4 derivatives, and then finally, what are we putting in this blank space as a y? So everybody buy that that's the derivative of, the derivative of, the derivative of, the derivative of y. So if I just think of all this as being multiplication, then I have d to what power? To the 4, and how many y's do I have? Just 1 at the very end. Now this is a little bit of an abusive notation because technically dx we're thinking of as one symbol, and so it really should be dx, 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 which is dx to the 4, but we're lazy and we just don't write the parentheses. So this is why the 4 looks like it's in 2 different places. Okay.
Quickly, like some sort of real-world example where
I don't have an example for the 4th derivative. I think in the packet someplace, maybe it's still there. The 3rd derivative though, the 3rd derivative, anybody know, like if you got a position function, what's the first derivative? Like if you have a height function, what's the derivative of height called? Is velocity, right? First derivative of the position is velocity. What's the second derivative of position? Is acceleration. The 3rd derivative of position does have a word. Anybody know it? Who said it? It's called the jerk. Right? The 3rd derivative is called the jerk. When you have a very sudden change in acceleration, you feel a jerk. Like imagine you're in your car and you get rear-ended. You have a very rapid change in acceleration, and you feel this thing that we call the jerk, right? And even like if you ever sleep, but kind of asleep, and then you like just wake up with this jolt, Like there's a name for that phenomenon when you sleep. I think it's called the myoclonic jerk, and it's again this very sudden. I think I've got that word right. Do you know this word? Is it hypnic jerk? I have no idea what myoclonic is. I'm just haven't looked at this in a long time.
I like that better though.
We can look up myoclonic. It might have nothing to do with anything. Hypnic jerk maybe is it. Yeah, and so the third derivative of position is jerk. I don't have any context for you for a fourth derivative. Yeah, something profane, because if the third derivative you're calling somebody a jerk, then it can only escalate from there. Snap, crackle, and pop. Good. Okay, number 3, we introduced a concept known as concavity. Let's write the intervals of concavity for these 3 graphs. Here we go. This first graph, we are going to say that this graph is concave up on all real numbers minus infinity to infinity. Concave up. And the second graph is concave down. Again, on all real numbers. The third graph is a mix of concave up and concave down. In the beginning part, until we get to the origin, this piece right here, does that look like the first graph or the second graph? Looks like the second graph, this piece in particular. And so this graph right here is concave down from minus infinity to 0. And then this graph looks like which one, the first or second? Looks like the first, and in particular, it looks like this piece of the first. And so this graph is concave up on 0 to infinity. It's the same thing we said about the derivative and increasing, decreasing. So you can include 0 if you want. You could not include it if you want. Okay, so let's just talk a tiny bit about the behavior of these graphs. This function right here, increasing or decreasing? Decreasing, and then from here, increasing. So that's the first derivative behavior, right? What kind of slopes do you have on this side? Negative. And what kind of slopes do you have on that side? Positive. So there's a change in behavior as far as the first derivative is concerned, right? But let's just take a look at a few of the tangent lines, a collection of these tangent lines. Let's say that one, and that one, and that one, and that one, and maybe one more. Ballpark, slope for this first tangent line on the left. -3 is fine. Next one. -2, bottom. 0 over here. 2 and 3. If I just look at that collection of numbers, -3 and -2, 0, 2, 3, is that collection increasing or decreasing? It is increasing, and it is a steady increasing, right? That is not a change in behavior. And so that collection of numbers, the way that those numbers are changing is the second derivative, because I'm just looking at this collection of numbers which represents the first derivative. Derivative is the slope of the tangent line. So these numbers are outputs for the first derivative, and these numbers are increasing. But I know that if a function is increasing, then its derivative has to be a positive thing. And the black collection of numbers is increasing. And so the derivative of this collection of black numbers must be positive. And the derivative of that collection of numbers is the derivative of the derivative, which is the second derivative. And so what's consistent in this entire graph is that the second derivative at every one of these points is positive, because these numbers are all increasing. Let's take a look in the next picture. Tangent line, tangent line, tangent line, tangent line, tangent line. Slope of the first one, 3, and then 2. Somebody said 1, that's not right. All right, let's see. Oh, sorry, negative, thank you. Okay, and what can you say about that collection of numbers? They are decreasing. And so in this first picture, y double prime was positive the entire time. In the second picture, y double prime is negative the entire time. The collection of black numbers, which is a derivative, is decreasing. So its derivative must be negative. Okay, and then in the second one is where things change. On this piece of the curve, the graph we said was concave down, which means what's true about y double prime? Careful. But y double prime is negative. Yeah, and we got to, like, there's just so many options here with new words with increasing, decreasing, positive, and negative, concave up and down. So on that space, the second derivative is negative, and on this space, the second derivative is positive, okay? So two separate things to keep track of now, increasing, decreasing, and also concave up, concave down. And they're really like not related to each other. Okay, so a little cutesy mnemonic device to help us remember which is concave up and which is concave down. Note that if a graph can hold water like a cup, then the function is concave up. That first guy holds water, concave up. I got it? Cup, C, up, concave up. Okay, and the second graph, if a graph looks like a frown, then the function is concave down. So there's your frown. Now most graphs are collections, combinations of those two kinds of things. And so you got to make sure you see that in the beginning part, this guy right here is part of what? Part of a frown. So you don't need to have the whole frown for it to be concave down. This guy is part of a cup. You don't need the whole cup for it to be concave up. Now my holding water business, like it kind of like, you know, the water will clearly trickle all the way. So like you got to be careful. You don't need the entire cup, right? It's just bits and pieces. Okay. On the next page, let's fill in a few blanks here together. If f prime is positive, then the graph of f is what? Let me give you some choices. These four blanks, I'm going to give you the four choices in no particular order. Concave up, concave down, increasing, decreasing. Those are the four choices. Concave up, concave down, increasing, decreasing. If f prime is positive, what is it? Concave up, increasing, increasing. This is a first derivative answer. First derivative tells you about increasing and decreasing. If f prime is negative, then the graph of f is decreasing. Okay, so first derivative always tells us about increasing and decreasing. If f double prime is positive, then the graph of f is concave up. And if the second derivative is negative, then the graph of f is concave down. I don't know. I don't have a good answer for you on that one. Is why don't we use concave and convex? Yeah. I'm actually not a fan, but it's my go-to example. Yeah, okay, so do we know the words concave and convex? One of these shapes is concave and the other is convex. Which one is concave? First one or second one? Yeah, first, yeah, this one right here is concave. And this one over here is convex. Yeah, I don't know. So how would you use one of these words, Matt, to describe, I don't know, like either this shape or this shape? Yeah, and Levi said something about the orientation. Yeah. Yeah, I don't know. But these are the words we use.
Is it because the value as it's going up? It's like, how to explain that? I had an idea of how to explain it.
All right, let me know if it comes back to you. Okay. All right, so the second derivative in and of itself is not a complicated concept. It's just a derivative of the derivative We discover here it doesn't have to do with increasing and decreasing, but rather it has to do with concavity, concave up and concave down. But by virtue of now having information you need to know about the first derivative captured in the first two blanks, and now new information you got to keep track of for the second derivative captured in the third and fourth blanks, your job has become harder because now you are responsible for knowing more stuff. So the second derivative isn't complex, but it adds to the pile of things for you to keep track of now. And that's where the difficulty arises. Just keeping straight what derivative am I looking at and what information does that give me. All right, activities are there. I will walk around, take out any old homework you have. I haven't checked in a few days. So take that out and let's see how far we can get here.